Right, everyone, this is the second half of our 3.4 concepts review. We're still looking at derivatives and velocity and motion. Remember, this is all from a calculus point of view, so I don't want to make you physics devotees upset about this. But here we go. Okay, so this is the next part where we're looking at this function in terms of the data generated by a function rather than the function or the function's graph. The values of the coordinate s of a moving body at various values of t are given below. So this is a very typical thing to do on an AP calculus exam, just give you a bunch of coordinates rather than giving you a function. So the first thing to do is to plot s versus t and to sketch a smooth curve. So let's get started on that. Go ahead and do that, and I'll come back with my answer too. So take a minute, graph those points. So here's my smooth curve. I know what you're thinking. It's probably not what you drew, and I kind of do this for a reason. Usually when I see students drawing their curves here, they try to make, clearly this point right here, I think it's that t equals 2. It looks like that should be a maximum. But there's actually nothing in the table of values to indicate that it is the maximum. The maximum could happen before or after this point. We don't actually know. So when I draw my curves, I like to emphasize that we don't know if this is actually the maximum. And to draw that as a maximum exclusively would be doing a disservice to the data. So here is mine. Maybe yours doesn't look like it, but as long as it's a smooth curve, I think it should be fine. So the first one, estimate the velocity at t equals 0.5. So remember that velocity at 0.5 is velocity at 0.5 is, well, the velocity at any place is the derivative of position. And the derivative is always just a slope. So you need to, if you're going to estimate the derivative any place, you're basically just finding the slope. So you can find any 2 points which are close to 0.5 and use those 2 points to estimate the derivative. Maybe you want to use t equals 0 and t equals 0.5. Maybe you want to use t equals 0.5 and t equals 1. Maybe you want to use t equals 0 and t equals 1. That's usually the one that most people are going to go for. So I'm going to go for that. T equals 0. So this is the derivative of position at time equals t. That is equal to the position at tb minus the position at ta all over tb minus ta. So if I want to do the velocity at 0.5, that could be approximated with, and what did we say, s of 1 minus fs of 0 over 1 minus 0. What are those two numbers? 30.2 minus 40 over 1. So I think that looks like negative 0.8. Negative 0.8. How about at 2.5? Okay, at 2.5, that's right here in the chart. So if I wanted to estimate that one, use any 2 points that are near that. I'm going to use 3.0 and 2.5. There's no rule that says I can't use those 2 points. So this is going to be s at 3 minus s at 2.5 over 3 minus 2.5. And you might be saying to yourself, but if we can choose any of those 3 different pairs of coordinates, won't we get a bunch of different answers? Yeah, you will. But does it matter? No, it doesn't matter because all of them are going to be close and you all use the good method for evaluating or estimating that derivative. So whoever is looking at your paper has got to look for 3 different answers on a question like this if they were smart. All right, what is 38.2? What is it at 2.5? That's 45. And this is over 0.5. Let's see if I can do this subtraction in my head. 38.2 minus 45, that is negative 6.8. All right, let's check with Alexa. Computer, what is 38.2 minus 45? Ooh, ignored.
38.2 minus 45 is minus 6.8.
Woo! Minus 6.8 divided by 1/2 is what? Negative 13.6. So this is approximately negative 13.6. To avoid redundancy, I'm not going to do 3.0. At what values does the particle change direction? Okay, so where does it have to change direction? Okay, if we know that we don't know what the position graph actually looks like, the truth of the matter is the particle could change direction at any point. But where does it have to change direction? Well, it has to change direction someplace around here. Why there? Well, here we know that the particle is losing position and then gaining position again. So somewhere between t equals 0.5 and t equals 1.5, we have to have a change in direction. Also, someplace between, well, let's actually go about it a different way. You might be tempted, based on my graph, to say that it has to be someplace between t equals 2 and t equals 2.5. Between 2 and 2.5. And that's not exactly true either, because remember, we could have drawn this where, the peak was on that side. That's equally valid too. So we actually have to say that there is a maximum, or no, that's not what I wanted to do. Get out. No. We have to say that there is a maximum somewhere between 2.5 and 3.5. Okay, so approximate values, well, any value between 0.5 and 1.5. I don't know, let's say at approximately t equals 0.8. If someone's really reading your work, they'd have to accept any answer between t equals 0.5 and t equals 1.5. Where is there a maximum? Well, again, we have to, it's any point, it could be any place between t equals 1.5 and t equals 2.5. Why don't we say t is equal to 2.6? You have to, there's a range of values that could be correct here. If this was an AP test, believe me, they would be reading for a range of values and not any particular value. Approximately when is a particle moving at its greatest speed? So I think I have this around, what is this? T equals 1, t equals 2, maybe t equals 2.2 or 2.1. This is all approximate. But let's just say it's near t equals 2, okay? Again, you're looking for where, if you're grading this, you're grading a range of values, you'd be looking for an answer that's somewhere between 1.5 and 2.5. All right, a few more to go. The position is given, the position x coordinate of a particle moving along a horizontal line y equals 1 is given by this. So it's on the line y equals 1 and it's moving left and right. Using analytic methods, determine when the particle changes direction of motion and its position at each of these times. Okay. Let's remember that a particle changes direction only if its velocity is equal to 0. Undefined too, but I don't think this velocity is ever going to be undefined. So the first thing we're going to do is find the velocity function, which luckily for us, that's the same thing as the derivative. So that's equal to x prime of t. And that's equal to 3t squared minus 12t minus 63. Oh, and this is a factoring job now, isn't it? We want to set that equal to 0. Let's see. To make my life easier, can I factor out a constant? And I think I can. I can factor out a 3. So factor and divide it. We get that t squared minus 4t. Ooh, what's 63 divided by 3? I think that's 21. Minus 21 is equal to 0. Do a quick factoring job here. I think that's t minus 7t plus 3. Okay, let's see. Do any of these are really critical values, but t equals 7, t equals negative 3. Do any of those clash with our domain? And I'm seeing t has to be greater than negative 10. Both of those values are greater than negative 10. So we're just going to put them down here. Negative 3 and t equals 7. What is the x-coordinate at those? Just go ahead and calculate those, and I won't bore you with my calculations. Presto. One thing that we should be aware of is that since these t equals negative 3 and t equals 7, since those are both places where the velocity are equal to 0, those are places that are also candidates for the leftmost point and the rightmost point. Okay, so it's very possible that 228 is the furthest to the right that this graph will get, and it's also possible that when t equals negative 272, that's the furthest left that this graph will make. Or at least they will be local minimums and local maximum. Come to think of it, we've got a cubic function, and for a cubic function, the domain is, or the range is all real numbers. So I think these will only be local minimum and local maximum. Now, on number 5, it says to graph the parametric equations that you see there in a window that is very specific, negative 400 to positive 400, negative 1 to 2. And use trace to confirm the results that you did analytically. I think I'm just going to let you... No, I should probably do that. Let's go ahead and put those functions in our parametric mode in our calculator. Here we are going to parametric mode. Here are the parametric function in our y equals menu. Here's our window, and let's graph. Whoa! Keep going the other direction, buddy. Whoa! Turn around. Keep going. There you go. Okay, so you notice how that curve or the parametric or the path turned around in 2 different places, and I'm willing to bet that it turned around when t is equal to negative 3 and t equals 7. Next, we're supposed to use a trace function to figure out when it turned around. So I'm going to push trace right now. Did I push trace? Yeah, I think I did. And let's just fast forward. I don't want to, mess around here. Let's go to when t equals -3. All right. And look down over here. Notice that t equals -3. The x-coordinate is 228, which is what we predicted with our analysis. I'm going to back up t to like -3.1, 3.2, and notice, look at the x-coordinate. It is increasing as we get closer to -3. And then now that we're at -3 and we keep increasing, that x-coordinate should start decreasing. Yeah, it does. Okay, so let's fast forward again, and let's get to when t equals 7. Actually, let's go t equals 6.5. Let's be smart about this. 6.5. Okay, 6.5. Look at the x-coordinate. It is -268, -269, -270. At t equals 6.9, we get -271. And there's that 272. -272, and then as t keeps increasing, notice that the x starts moving to the right. So that does confirm everything that we did analytically. The last thing to do here is you noticed how the graph was the path was stacked on top of itself a lot. Well, the suggestion here from the good folks at Pearson is that if you change that y-coordinate so that the y-coordinate gradually goes up, even though doesn't actually go up, but if it gradually increases, then you'll be able to see those changes in direction more clearly. So let's just play along with them. So we got t plus 0.1 t, and then it says to put a parenthesis, and then t greater than equal to a. Geez, how do we figure out t is greater than equal to a? Well, the greater than equal to button is actually under second math, and there's that greater than equal to. When math is greater than equal to a, and I think it said a is going to be our first change in direction, which was -3. And I think I forgot to put a t here. T greater than -3 plus 0.1 for t greater than equal to, and I can't read this, t is greater than equal to, and then that second place where the function turns around, which is 7. And looking back at it, I think I put a t where there shouldn't have been a t, which is here. Okay. So this is really the unknown for me. I don't think I've ever done this before, but I'm willing to do the experiment with you. Let's push the graph button, see what happens. Okay, moving to the right, and then, oh, look at that. It just popped up 0.1 units and started moving to the left, and then it's going to pop up 0.1 units again and move to the right. That's really interesting. Cool. Well, thank you, Pearson. That's a new one for me too. And folks, that's it. That's all we have for today. Hope that was a lot of fun for you. It's kind of fun for me, especially that last graphing over there. And I'll see you next time with more calculus review.